Thank you very much. So welcome to the, good morning and welcome to the second episode of the webinar series of the React cluster, where React stands for Resource Efficiency and Automation for Circular Transformation. The cluster is formed by different projects of the European Union Horizon program and mainly projects that are part of the Green Deal cluster. We have ALCHIMIA, CLARUS, Darrow, GRINNER, Reclaim, and Wood to Wood. Together with these projects, we have organized a webinar series, and this is the second episode. We already had the first one, and in this second episode, we will assess sustainability performance assessment, and this webinar has been organized by CLARUS. So we want to understand how sustainability has been assessed in different industries for the different projects participating in this webinar. So this is the agenda. We will have 4 projects of the cluster participating: CLARUS, Reclaim, ALCHIMIA, and GRINNER. And please address your questions in the chat, and we will discuss them at the end of the presentations. Also, we are recording this webinar for dissemination purposes so that we can share it, and you also can share it with whoever is interested in learning something more about sustainability. So let me present the first speaker, Roberto Rocca from CLARUS project. He is a postdoc researcher at the manufacturing group of Politecnico di Milano, and he is also the technical coordinator of the CLARUS project. He is involved in different European projects involved in the sustainable manufacturing and also in consultancy projects that are helping manufacturing companies developing LCA, so life cycle assessment methodologies, and environmental sustainability performance assessment methodologies. He is from the CLARUS project. CLARUS project he aims to to address the sustainability challenges in the food sector, combining the sustainability paradigm with the AI-based applications, with the final goal of developing a platform that assesses the resource consumption and traceability in the food industry, in particular water, energy, and logistics. And one of the outcomes of this project will be the Green Deal Index that will be more explained by Roberto. So I leave the floor to Roberto that can now share his screen.
Yes, thank you very much, Ludovica. Okay, can you confirm that you are seeing my presentation? Okay, so thank you very much, Ludovica, for the introduction. Good morning to everyone. As anticipated by Ludovica, my name is Roberto Rocca, and I'm from Politecnico di Milano, and I'm actually a researcher, a postdoc researcher in the manufacturing group, and I'm also involved as a technical coordinator of CLARUS project, since Politecnico di Milano is the coordinator of the project. I will introduce in the next minutes this presentation that is related to the Green Deal Index for environmental sustainability assessment for the food industries that represent one of the tangible expected outcome of the CLARUS project. So this is the very brief agenda of the presentation. I will introduce very shortly the concept of sustainable manufacturing and how CLARUS project is positioned in the current sustainable manufacturing paradigm that is involving manufacturing industries. Then I will show you some insight related to the Green Deal Index and the sustainability matrix that we have developed in CLARUS and that we are going to test in this final part of the project, showing a couple of examples of this calculation related to this index, and finally a few conclusions related to the presentation, and of course some minutes related for any curiosity questions that I will answer at the end. So the preliminary consideration that I would like to introduce before speaking about CLARUS is related to the concept of manufacturing decarbonization. We know that a lot of industrial sectors are dealing with the challenge of sustainability and sustainable manufacturing, and the concept of manufacturing decarbonization refers to the capability of manufacturing companies to lowering the environmental impact that are generated by the different processes that involve companies within the factories and also outside the factories along the supply chain. And if we want to summarize the main area in which manufacturing companies are investing and putting the majority of their effort in order to lowering the emission of the environmental impact due to the consumption of natural resources, we can summarize this area in the 7 bullet points that you find in these slides that are the adoption of digital technologies, so the integration of the concept of Industry 4.0 and Industry 5.0 within manufacturing processes, and the capability of the companies to build ICT architecture and data spaces to manage environmental sustainability data. The paradigm of servitization together with the circular economy in order to decoupling the economic growth of the companies from the resource depletion utilized for manufacturing product and services, energy efficiency, and the capability to measure environmental sustainability parameters of suppliers, so the concept of green supply chain, green procurement, but also the capability to measure the performances of the consumption at the production process level, so the sustainability measurement and process decarbonization. And if we would highlight which of these areas are involved in the CLARUS project, for sure, the adoption of digital technologies in order to build a data space for achieving better performances in the field of energy efficiency together to the sustainability measurement are the main area that we have studied in the CLARUS project in order to develop the CLARUS solution. So, starting from this consideration, we can summarize that CLARUS involved, from one side, the sustainability paradigm of manufacturing companies together with the digitalization of the production processes. And this twin transition in CLARUS find place in the convergence between the artificial intelligence technologies from the digitalization side with the improvement of sustainability performances from a sustainability perspective. So, according to this convergence that try to develop the CLARUS solution, the main key important role within the project is represented by the data. The data that are related to the consumption and the depletion of the natural resources that are utilized in the manufacturing processes of the project. So, since the adoption of digital technologies like artificial intelligence, but also cyber physical systems, IoT, and many other type of information and operational technologies can allow to the companies to manage the data in a better way in terms of flexibility, optimization, and reliability. In this case, in the case of CLARUS project, the main scope is related to the environmental sustainability data that we can intend as the source of information that are strictly related to sustainability, with a strong focus, of course, on environmental sustainability, because the main scope in CLARUS is to improve resources like energy, waters, and materials, Data that, if we correctly collect, analyze, and trace, can allow to the companies to improve the overall sustainability performances and then at the end achieve a better decarbonization level. And of course, all the things that I have said until now can be generalized for any type of manufacturing sector nowadays, because we know that the main objective of European Commission is to decarbonize the entire society. CLARUS project is related to a specific sector, that is the food sector, that is one of the sector that, of course, is gaining the major attention on sustainability paradigm because of many reasons that I don't want to explain in detail now, but I think that all of us knows very well. First of all, we are continuously growing around the world. We have overcome the 8 billion people in the globe, and is forecasted that we will reach 10 billion people until 2100. There is a big problem, a big issue related to the consumption of natural resources to feed all these people around the world, and there are, of course, many other environmental and social issues that characterize the food supply chain, like the management of the cultivation, the waste production, and of course the emission of environmental pollution along the supply chain. So because of these many reasons, of course, the attention related to sustainability in the food sector, as we know, is very high. So considering this convergence between digitalization, in particular artificial intelligence, and sustainability performances applied to food sector, this is the main boundaries of the CLARUS solution. In fact, the project is related to the optimization of the production and logistic resources in the time-critical bioproduction industries in Europe, and is a project from Horizon Europe program in the call of Digital Emerging 0109, that is AI, data, and robotics for the Green Deal. And the target of the CLARUS project is related to the non-robotic outcome. So we already understand that there is a strong connection from a sustainability perspective to the Green Deal, that we know is the biggest sustainability program delivered by European Commission. The project has been started in 2022 and will finish in the next month. So we are actually in the final part of the project where we are finalizing and testing the solution that we have developed. This is the consortium of the project. We are 3 universities, Politecnico di Milano, that is the coordinator, Tampere University, Università Politecnica di Valencia, one large enterprise that is engineering, that is the provider of the IT component for the building of the data space, Ikerland and No Center as research centers, Expert AI, that is a small medium enterprise that manage the ethical and legal aspect related to artificial intelligence, and the 2 pilot of the project that are Onkayoki with its associated company GMM, and the second pilot that is from Spain, that is Ardo company. So the objectives have been already declared by Ludovica firstly, and then by me in the previous slide. And as we have said, the main objective is to build a unique IT platform, so a solution with high communication and processing capabilities that rely on the concept of data space and artificial intelligence from a digitalization point of view, in order to improve the Green Deal performances through the Green Deal Index within the parameters of natural resource consumption of the 2 pilots. As I have said before, the 2 pilots are Onkayoki from Finland that is a company that produces pet food from the waste discarded by the slaughterhouses in the countries. While the second company, that is Ardo, is a big company from Spain that produce and sell frozen vegetables around the world. So two pilots that produce different type of product, but of course that have a lot of similarities from a production process point of view in terms of optimization of natural resource consumption. The schema that you see in this slide represent the main approach of the project. In fact, the main scope of the project developing this unique solution, this unique platform, is to produce three tangible expected outcomes at the end of the project. These three outcomes, expected outcomes, are from one side the Green Deal Index that represent the final indicator able to assess the improvement of the sustainability parameters analyzed within the project. The second tangible expected outcome is the CLARUS AI toolkit that represent a set of mathematical model and machine learning and artificial intelligence algorithm applied to improve sustainability performances of the project. And thirdly, the third outcome is the CLARUS data space. That is the overall infrastructures, technical, so physical infrastructures, but also logical infrastructures in terms of data management that represent the environment in which all the environmental sustainability data of the pilot are managed. And of course, the pilots represent the main pillars that provide the data and the processes to be optimized. So this is the overall approach of the project, able to deliver these three tangible expected outcomes. And of course, these three tangible expected outcomes are totally linked together one and each other. So if we would like also to summarize the connection between these three tangible expected outcomes, as we have said, the Green Deal Index represent the final indexing and ranking of the pilot parameters. Of course, the data space represent the overall environment able to harmonize and transform all the data analyzed in the project, while the AI toolkit, that is the other tangible expected outcome, represent the algorithm trained and applied to optimize the pilot parameters. Moreover, a Green Deal ontology has been developed within the project in order to define the semantics and the logical interconnection of all the variables that are analyzed within the project. And of course, this Green Deal ontology doesn't represent another tangible expected outcome, but is totally related to the Green Deal Index calculation. So now I will focus this second final part of the presentation of the first tangible expected outcome, that is the Green Deal Index. The Green Deal Index, since CLARUS is totally close to the concept of the Green Deal, represent a final comprehensive indicator that we have developed in CLARUS and able to assess the improvement that the AI toolkit can allow within the variables that we have analyzed in the project. So if we would like to highlight a logical connection between the Green Deal Index, that is the first tangible expected outcome of the project, with the environmental sustainability data, we can summarize this connection in this schema. In fact, a Green Deal performance assessment methodology has been previously developed that represent the overall theoretical methodology able to gather the data to be analyzed for sustainability optimization, together with the Green Deal ontology that in parallel represent the overall semantics vocabulary to manage the data within the pilot. Then, according to the priorities of the pilot, or in general of the company under analysis, a set of indicators are selected, and thanks to a specific matrix of aggregation, the GDI is calculated. At the end, the GDI is utilized to analyze the impact of the AI toolkit before the application of the CLARUS solution and after the CLARUS solution. So it's a sort of thermometer able to measure the impact of the AI, so of the digital technologies and the data space within the production processes. Now, I don't want to go too much deep in the methodologies, but is the overall schema of the theoretical methodology developed in CLARUS that comprehend different set of sustainability metrics like life cycle assessment, circular economy performance assessment methodology, water management, energy efficiency, and so on. Of course, one of the main issue of sustainability metrics is to manage different sources of data and different type of variables. So not all of these data and information are required to be analyzed for every company. So starting from the overall theoretical methodology, a set of indicators are selected and utilized to calculate the GDI. GDI that at the end is utilized, as we have said, to assess the impact of the improvement of artificial intelligence. In parallel, as I've said, we have developed the Green Deal ontology that represent the logical connection and semantics of all the data that we have analyzed within the project. Why is so important to develop also an ontology in a context like CLARUS project? Because having a Green Deal ontology is, from one side, an advancement of the state of the art in terms of ontology concept development, and from the other side, can be utilized as a methodological guide for new scenarios. So if we want to think how to exploit CLARUS also in other environment after the end of the project, having a methodology like the Green Deal ontology can help new companies to detect the correct environmental data to be utilized to calculate the Green Deal index, and so facilitate the process of calculation. This is the overall schema of the GDI calculation. So the indicators that are selected within the processes comes from different level of priorities: environment, enterprise, process segment, and equipment. So there is a hierarchy of indicators that is analyzed within the company. And then, thanks to a process of aggregation, selection, grouping, and normalization, the final indicator is calculated. So, of course, the identification of the indicators starts from the Green Deal priorities from one side, but also the priorities of the single companies that is calculating the GDI. Then the weighting of the indicators is carried on thanks to the analytical hierarchy process as methodologies, and then a normalization is calculated in order to have the right weight of the different indicators that at the end are combined in the calculation of the Green Deal index. So this is just an example from one scenario that comes from the Ardo company. This is the list of some of the indicators that we have selected together with the with the company, like decrease of equivalent CO2 emission, the improvement of the performance of the freezing installation, since is one of the process that has been analyzed, or for example, the increase of the availability of the freezing installation equipment. So as you can see, this set of indicators are part of different hierarchy levels of the company. Start from the environment, that is the higher level of indicator, until to the equipment. For example, to the single equipment related to the freezing installation. And this is the logical connection that represent the relationship between the Green Deal ontologies, the environmental sustainability data, and the process where the data come from. So, for example, in this case, this is an example of the summary, we can say, of the application of the Green Deal ontology for the calculation of a single indicator. In this case, the indicator is the energy efficiency that is part of the enterprise level of the KPI scale, and these are the different measurement attributes that are utilized to calculate the energy efficiency parameters. So, for example, the total active energies, the active power of the pumping system, the active power of the compressor, and so on. And of course, all these measurement attributes are characterized by unit of measures and are related of a series of substances, so a series of natural resources consumed in the process, like hot water, cold water, ammonia, and so on. Moreover, the Green Deal ontology allows to track and trace the supply chain of the data that at the end we need to calculate the indicators. So the processing equipment, the planning processes, and the different steps that are related to the substances that we measure to calculate these indicators. And of course, this process of application of the Green Deal ontologies to track and trace the data and to calculate the single indicator is replicated for all the indicators that at the end are utilized to calculate the final Green Deal index. So also here, very briefly, you can see an example of the GDI calculation. So for each indicator that has been selected according to the priority of the industrial pilot, we have measured all the value exploiting the Green Deal ontologies, and we are weighting all these indicators according to the aggregation method that I've explained before. So at the end, thanks to this weighted sum, the GDI is calculated on a scale, on a percentage scale, in order to measure the sustainability status before the CLARUS solution and after the CLARUS solution. So we are now at the end of the project, so we are now measuring the GDI of the to-be situation. And at the end, we have decided to utilize this traffic light system with different color, red, orange, and green, in order to highlight the improvement of the GDI calculation. Okay, so I will conclude here the presentation, and I will leave the space for any questions or curiosity, but I don't remember. I asked to Ludovica if we manage now any question or curiosity, or at the end of the session.
Yes, thank you, Roberto. We can manage the questions at the end of the sessions.
Okay, perfect. So thank you very much to all for the attention. And I leave the floor again to Ludovica or to the second speaker. I don't remember.
Yes, I share my screen again. Okay, so the second speaker from Reclaim project will be Fredy Raptopoulos. Fredy is a senior engineer at Robenso and a roboticist and material expert with a master's in advanced production, automation, and robotic systems. He has expertise with the state-of-the-art machine learning and computer vision technology for material recognition, localization, and categorization. And he also has a long experience with robotic material recovery systems, which is also the context of Reclaim project. As Reclaim has developed the world fully first automated, low-cost and high-powered robotic material recovery facility, a facility that can be deployed anywhere. So to undertake what is the decentralized material recovery activities for the recovery of recyclable materials. So I will leave the floor now to Fredy for his presentation.
Thank you, Ludovic, for the introduction. Let me share the screen. So hello, my company Robenso is developing robotic sorters to address the waste management sector. And as part of the Reclaim project, we have developed the portable robotic material recovery facility, where I will talk about the sustainability performance optimization. At the right image, you can see the PRMRF installed at the island of Kefalonia. This photo was captured 20 days ago. We are also at the final stage of the project, and where we will deploy the machine at the final destination. And the idea of the portable robotic MRF, as very well stated by Mr. Komninos at the project panel, came from the unique geographical characteristic of the islands and of Greece, and the difficulty of applying the modern models of waste management that are implemented in other countries. It's very hard to implement them at remote places that Greece is full of. Those remote places, the practice that they follow today is either landfill the recyclables to the earth or transport them to the mainland. In Kefalonia, where the system was installed, the municipality loads the recyclables on trucks and transports them to the mainland with ferry, and then we have another 2-hour journey in order to transport them to the local MRF, where we try to recover as much as we can. And about 30% of the total amount is the residue, where we have to transport it back to Kefalonia because no one wants to bury the landfill waste in their earth. So this system was developed in order to be able to manage small quantities that remote places produce with seasonal peaks due to tourism. And I have a short sketch here of how the system is. We have a main conveyor belt, a 12-meter conveyor belt, where we have a vibrating surface in order to feed the conveyor belt and spread the recyclables across the conveyor belt width. Then we have an AI, HSI camera and RGB camera with an AI classification system in order to categorize the recyclables. Then we have 3 1.5 degrees of freedom linear robot sorters. Those are the robots that my company produces, and I will present them in the following slides. We have also the blowers, the valves, and the filters for the vacuum system in order to pick the recyclables. We have a magnet in order to recover the ferrous containers out of the mixed stream. And then we have another set of an AI of an RGB camera and 2.5 degrees of freedom robots, where we try to clean the conveyor belt as much as we can. We have 12 bins, 6 are the first set of robots and 6 are the second set of robots, and we also have looping conveyors in order to be able to loop the material if the material is good and if there is need for it. Here we have a video of the robots in action. This system is the 1.5 degrees of freedom robots. Those robots have a servo-actuated X-axis for traveling across the conveyor belt width, and then we have a pneumatic system for the vertical transition of the recyclables, and that is what it makes it a really low budget and cheap system, because we have the lack of more complex architecture, and we also have a very low mass of moving mass. Those are the 2.5 degrees of freedom robots, where basically it's the same system as the 1.5, but we have it bolted on a moving platform, and with this way we can be sure that while the vacuum happens between the suction cup and the recyclable, they have the same speed. The recyclable and the suction cup have the same velocity, so there is no drift, and we have better success ratio. Those robots are placed in the end of the PRMRF in order to be more sure that we will have less residue as we can. We also have 4 bins on each robot. So these robots can classify in more materials, and the system can pick 120 picks per minute. That equals to up to 4 tons of recovered material per day at 3 shifts, 3 duty day. And we can, at this time, we can recover up to 7 materials, different materials. But as our libraries, our AI libraries grow, those numbers are going to grow too. So another thing that we have studied and is the convenient transportation, because this system is going to travel to remote places. So we wanted to make it as easier as it gets with the lack of special equipment. So we have 4 hydraulic legs that exceed from the structure of the container, and the hydraulic pistons grow, and we can lift the container and take it without the use of crane, but we also can install it as in the right video in the exhibition of Verdetech at Athens, very fast. The same happened in order to transport it to Kefalonia. This system is really fast, and we can feed the system with recyclables 2 hours after the transportation. The performance of the portable robotic MRF can be summed up at those parameters. We try to optimize the picks per minute, the rate of picks of our system. And we try to make it as high as possible in order to be able to treat more tons per day. We also try to have high success in order to have less residue in the end. There are a number of classes that recycled we try to optimize it and to make it grow as long as our libraries are getting bigger. And the purity of the recycled material has to be high in order to be able to sell this material in the market. This goes both to the categorization system that has to be high, but also to the accuracy of the robotic systems in order to be sure that you pick what you target. And we also have to have a convenient operation with no experts, and we have to make it convenient in order to be able to be operated by unqualified personnel that we're not going to find experts in the edge of Greece. Another tool that we have developed in order to monitor the performance is this interface where we can control the robots and start and stop the system. We can monitor the performance. Basically, we have sensors in the system, vacuum sensor and laser sensors, in order to verify that the peaks that we told the robots to do, the robots actually did them. So we have the feedback of success, and we can have also a real-time composition analysis of the mixed waste stream. And we have also this tool. It's the HSI RGB imaging fusion tool, where we can examine special cases more carefully and see what went wrong and why. And we have also developed, together with the Catholic University of Leuven, we have developed a simulation of the portable robotic MRF, where we can change the bin allocation. We can change many parameters in order to examine different scenarios. Those parameters are the materials price, so we can change the materials prioritization. We can also examine different grippers in different robots. KUL also developed grippers to be novelty grippers to be mounted on the robots. And with this system, we can analyze the performance and see what criteria optimized our system. And then we can feed the real system with those parameters. In the simulation, KUL has also developed a target planner that tries to optimize the efficiency of the system. It takes account the prices of the materials, the different location of the materials, in order to optimize parameters such as peaks per minute or euros recovered per minute if we apply a price at each material. We saw that with this target planner, we had an optimization of up to 20%. So we are trying to implement this target planner in the real robot controller, and it will be tested in the next visits at Kefalonia. That was my presentation. Thank you very much.
Thank you very much. Okay. So we can move on with the next speaker now. I will share my screen again. Okay. Okay, so the next speaker from ALCHIMIA project will be Federico Rossi, assistant professor at the Interdisciplinary Center for Sustainability and Climate at the Sant'Anna School of Advanced Studies. He specifically works on the application of a life cycle assessment methodology across various industrial sectors. One of his main projects is the GREENS project, which focuses on the development of a platform that processes data and indicators to assess the environmental sustainability of the Italian companies from a circular economy perspective. So he will present the role of the life cycle assessment in the ALCHIMIA project. ALCHIMIA is a project that is focusing on the metallurgy industry transition to sustainable and efficient steel production. We know that steel making is a very energy intensive sector, and ALCHIMIA aims to reduce this energy consumption, emissions and waste, but also ensuring high quality production to digital technologies, in particular AI optimization methodologies. So I leave the floor now to Federico.
So thank you, Ludovica, for your introduction. So the presentation I will show today is named The Role of Life Cycle Assessment in the ALCHIMIA project. That, as you said before, is a European project regarding steelmaking. First of all, I would like to say a few words about our institution. Sant'Anna School of Advanced Studies is a well-known research university who is proud to provide its students that have been selected with a competitive examination the possibility to study in a college with very high education programs like bachelor, master, and PhD, and also to be in touch with a very interdisciplinary and international research activities. And the school is structured in 8 institutes and 2 interdisciplinary centers. Among them, we have the Interdisciplinary Center on Sustainability and Climate that gathers people from other institutes who share their background towards addressing some of the most transdisciplinary research topics, that is sustainability and climate, for which we need both social and experimental sciences expertise. So our mission is under the framework of the Sustainable Development Goals for the year 2030 of the United Nations. And among the thematic areas that we are addressing, we have life cycle assessment, but also circular economy, decarbonization, biodiversity, and other topics that you see here in this slide. In this framework, we have the ALCHIMIA project, whose aim is to develop federated learning model for steelmaking and cast iron production plants. In our consortium, we have the CELSA group, who is a steelmaking company with several factories around Europe, and Fonderia di Torbole, who is in Italy, and it is a cast iron production facility. Basically, this is a very broad project, but life cycle assessment is playing quite an important role in the project. First of all, because it is used to calculate a baseline for the steel making and the cast iron production plants involved in the project. The baseline calculation is a picture of the current situation of the environmental performances of the plants. But then the real focus of the process is the optimization. Basically, we are now developing an optimization model in Python that allows us to improve the environmental performances of steelmaking compared to the baseline. The optimization model is now being customized for one of the factories owned by CELSA Group, but of course it is something that can be applied also to other steelmaking and cast iron production plants. At the end of the project, we will make a comparison between the optimized process and the baseline calculation. The process optimization will not just involve environmental impact aspects. There will be also economic indicators, but in this presentation we will focus only on the environmental optimization of the process. In particular, we will discuss the methodology that we will use to conduct this analysis, because the final results of the process optimization is currently under evaluation, and so they will be ready very, very soon. So just a few words about the LCA methodology. I think most of you already know it. LCA is a standardized methodology to assess the environmental impact of product, processes, and services through the entire life cycle. So considering the resource extraction and refining, the manufacturing, the packaging, use, and end of life. And according to the circular economy principle, at the end of life, products can be recycled so that the materials can enter again in the technosphere. LCA therefore accounts for all the materials and energy consumption involved in the life cycle of the process, and all the emission and waste generation. And so this is basically a computational model that then has as inputs all this data, and as outputs return some environmental indicators like the carbon or the water footprint. As I said, the application of LCA in this project is the steel making. In particular, two main steel making pathways exist. The primary route, which is with a blast furnace, which converts iron ore into steel. And the secondary route, which is basically the steelmaking production from scraps, so from waste that are melted to produce new steel. Of course, this is a complex process which involves an electric arc furnace, a ladle furnace, a ladle and a ladle furnace, and casting, which is not the object of ALCHIMIA, but it is also an important phase of steel making. And in all these steps, basically we have inputs from materials, energy, and we produce waste, emissions, and byproducts. So here's a short summary of the inputs and the outputs that may be involved in the process, but of course they can be really different. Here we have, so we just displayed some examples. So going back to the goal of the study, as I said, the idea is to improve the steelmaking process using LCA. From the methodological point of view, we have two main options. The first one is to conduct a scenario-based comparative life cycle assessment. Basically, this is the most widely used approach, which basically consists of creating scenarios by playing with the parameters of the model. In the specific case of this analysis means to play with materials and energy inputs to find the optimal, materials consumption to reduce the environmental impacts. It is evident that since the number of materials involved in the process is very high, it would be very difficult to create scenarios that really cover all the options, because it would imply the creation of a very high number of scenarios. Therefore, in ALCHIMIA, we are using an alternative approach, which is the optimized life cycle assessment, in which we use math to calculate the optimal solution. So the idea is to use optimized life cycle assessment to solve a decision-making issue, which is basically determining the optimal mix of scraps and ferroalloys that minimizes the environmental impact of the steel making process. Optimized LCA is a name that we gave to this methodology specifically for this project, but it is not a recognized methodology. The methodological guidelines for LCA are the ISO standards. So basically, we adapted the ISO standards that are typical of traditional LCA to the optimized LCA methodology. For instance, in the goal and scope definition, we need to define the objective function that shall be minimized, which shall be, of course, coherent with the objective of the study. In the life cycle inventory, there is basically the quantification of input and output flows. We need to define what are the optimization variables that shall be calculated by the model and what are the parameters that shall be set by the developer. In the life cycle impact assessment, which is normally the calculation of environmental impact indicators, in this case, we minimize the objective function. So we minimize one or more than one environmental impact indicator. And at the end, the interpretation is very important because, of course, the optimization model will return a solution that may be not realistic or not practically feasible. And for this reason, it is important to check the consistency of the results. Here is a summary of the main methodological choices that can be taken in the mathematical formulation of the optimization process, but I won't bother you so much with the mathematical formulation. Here's in this slide, I would like to represent with a chart, with a flow diagram, the difference between the scenario-based comparative LCA and the optimized LCA. So in the scenario-based comparative LCA, we follow the 4 steps of life cycle assessment, and we create multiple scenarios with by playing with the life cycle inventory parameters. Differently, in the optimized LCA methodology, some of the parameters become actually outputs of the model, so they become decision-making variables. So we don't have the creation of scenarios, but we have the calculation of environmental impact factors that are associated to each parameter and variable. So for example, if one of the parameter is the consumption of aluminum, let's say, the environmental impact factor is the environmental impact of 1 kilogram of aluminum. So these values are processed with an optimization model, and at the end we get the optimal decision that minimizes the environmental impact. Of course, the comparison between the scenarios is in this case replaced by a consistency check, because the model basically does this comparison instead of us. So here is a summary of the variables. So according to the goal of the studies, the variables of the process are the scraps, of course, but also all the other materials that are added, like aluminum, ferroalloys, vanadium, titanium, or I don't know, the carbon sources like coal, other minerals like dolomite, or also the electricity consumption and the consumption of gases like methane and argon in the ladle furnace. Other materials are set as parameters like water consumption or wastewater production, slugs, dust that are waste or co-products of the process. So these are set as parameters because they are not calculated by the optimization model. We also need to set some constraints, and in particular, our colleagues from the TECIP Institute that are collaborating with us on this, are developing the machine learning correlation that are used to make sure that the quality of the steel output is the one required by the final consumer of the steel, which is very, very important. But there are also other correlations. For example, electricity consumption is correlated to the type of materials that we are melting. So we are also implementing a mass balance and energy balance constraints. The environmental impact factors are calculated with the software CIMA Pro, which is a widely known software for life cycle assessment, and the optimization model is based on Python. The life cycle impact assessment phase is the minimization of one of the environmental impact categories proposed by classic, let's say, life cycle impact assessment method, like the environmental footprint one. Of course, we could optimize in principle a lot of different indicators, but the literature suggests us what are the most relevant indicators that shall be considered and prioritized in the steelmaking sector. So, accordingly to the goal of the study, we may decide to minimize one by one all these indicators, or maybe select only one of them, or maybe to make a normalization and weighting to calculate a single score from these categories, and so minimize all the overall environmental impact. Of course, this decision is also subjective. So in the following of the project, we may decide to compare the results obtained by if we change the environmental impact category to be minimized. And at the end, we will make a consistency check. So with the support of the metallurgists and the experts in the consortium, we will check the results of the optimization model and validate it. So as a few take-home messages, the integration between LCA and mathematical optimization is possible, and it is a methodological challenge that has been addressed in this presentation. So in this case, the approach is applied to the optimization of steel scraps and ferroalloys. We used optimized LCA to reduce the scenario complexity and prevent us to the need of making a lot of scenarios that cover all the options. And as a future development, as I said, so basically we will compare the results used with the traditional comparative life cycle assessment. We will perform a sensitivity analysis on the main methodological choices regarding LCA, and we will check the consistency of the results. Thank you all for the attention. I would also like to thank all the partners involved in ALCHIMIA. We are having a really great collaboration with them, especially with our colleagues of TECIP Institute from Sant'Anna School of Advanced Studies, and with which we are having a very close and fruitful collaboration. Thank you very much.
Thank you very much, Federico. Okay, so we can now address the last speaker. Yeah, okay. Sorry. Okay. So the last speaker will be Nikos Panagopoulos. He is a senior engineer at Tech Hive Labs and part of the GRINNER projects. In particular, he has more than 9 years of experience in developing hardware and firmware for embedded systems for non-destructive testing technologies. And he also has proven track in high-speed data acquisition and mixed signal electronic design for compact and resource-constrained systems. He has high expertise in robotic inspection and condition monitoring application. And today he will present how and why to calculate the environmental cost of reducing fires in e-waste recycling facilities. So the importance of life cycle analysis in the context of GRINNER project. A few words for GRINNER project. GRINNER is a project that aims to commercialize an autonomous AI-enabled sorting system, which is capable of detecting and removing e-waste, in particular batteries, from the waste streams that are entering machines that crush the consolidate waste, because this type of products can be very dangerous in terms of risk of fires. So I will now leave the floor to Nikos.
Thank you very much for introduction, Ludovica, and good morning from me as well. I will just share my screen now. Okay, I believe you can see my screen.
Yes.
Great. Yes, so my presentation is about the GRINNER project, and more specifically, how and why to calculate the environmental cost of reducing fires in e-waste recycling facilities, and the importance of life cycle analysis in the context of the GRINNER projects. We'll just talk a bit about the Tech Hive Lab. So my company is a research organization based in Athens, Greece. And in this project, we led the development of the system that I will show you in a bit. I have sectioned my presentation in 4 parts. For the first one, I will talk about the problem of fires in waste facilities, what they are and why is it important that we solve it. Then I will present to you with some current state-of-the-art solutions and how GRINNER fits in the landscape. The third part, we'll talk about lifecycle analysis at a high level and how it fits the GRINNER project and GRINNER system, how it helps us. And I will summarize in the end with a final slide. So for the problem of fires in waste facilities, I would like to show you a very nice animation video that our marketing team has produced and explains the concept very well in simple terms that everybody can understand. So we'll just now play the video, and I hope you can also hear the sound.
Wondered why you're asked to check if your phone or laptop battery is not overheating during a flight?
Batteries in electronic items have the capacity to store a lot of energy in a very small space, thanks to elements such as lithium. This is the reason we can recharge our phones and other devices so easily.
With technologies developing quickly, batteries are becoming more and more powerful, meaning greater energy in a smaller space.
However, there can be problems when they get damaged. The energy accumulated in them, if suddenly released, can create fires.
This is an issue not only for consumers, but also, and on a much bigger scale, for recycling facilities, where thousands of such devices are processed every day.
Such fires, at best, severely disrupt e-waste recycling processes, and at worst, can cause millions of euros worth of damage and serious injury or even death, affecting the lives and livelihoods of those involved.
A survey of e-waste processors revealed 36% had encountered a serious battery-related incident in the previous year.
As it stands, there is no available solution to eradicate the fires caused by these so-called zombie batteries.
That is where GRINNER comes in. The project will commercialize an AI-enabled sorting system capable of detecting and removing e-waste containing batteries from waste streams before they enter machines that crush and consolidate waste.
The system will comprise the high-speed energy-resolved X-ray detectors and an AI-enabled software module that will analyze X-ray data and effectively detect waste-containing batteries while it passes through the waste flow.
The project is developing a prototype system that will be installed in an e-waste facility to conduct live trials and test it in real-life circumstances.
GRINNER will have a positive impact on the environment as it will reduce waste from materials destroyed and minimize water contamination that occurs during fires, as well as preventing toxic gas emissions from such incidents.
It will also enable e-waste processors to save millions of euros every year by eliminating zombie battery fires and, most importantly, improve the health and safety of workers.
If you are interested in learning more about the GRINNER technology, get involved as a stakeholder.
Yeah, so as the video touched on, there are many consequences and implications from fires in e-waste facilities, and I will just detail them in more detail. One of them is repairing or replacing damaged equipment and infrastructure. This is a cost added to the business. Temporary interruption or cessation of activities due to fires, loss of materials due to burning, because of course recycling facilities also can make a profit from recycling the materials in the waste. Replacement of firefighting equipment. This can be either foams or destroyed sensors. Other associated costs, such as the treatment of water used during firefighting efforts, because obviously when you put out such fires, the water is then contaminated with all sorts of chemicals. Higher insurance premiums due to the incidents, and reputational damage and negative press as a result. Now, what can we do about these fires? For starters, some existing systems that are on the market use RGB cameras to detect fire or smoke on process lines. Another solution is thermal detection, where the infrared radiation from a thermal event can be detected. And then there are suppression systems such as automatic sprinklers or targeted extinguisher systems that have a camera and a blast and jet utilized to target the incident. However, the common drawback of the state-of-the-art systems is that they can detect fires only after they have started. And what is done currently to prevent fires is that workers are used currently to take out of the line items that they think contain batteries, so that they don't end up in shredders and further down the process line and result in fires. But what we aim to do with the GRINNER project is improve that prevention by a lot by installing an X-ray scanning system. This is a very high volume throughput system that can scan devices at speeds of belt speeds of up to 1 meter per second, and it can detect batteries in multiple devices by leveraging AI algorithms that our project partners have developed. And then the results of this detection can be fed into robotic systems or workers to be removed from the line. And because of this fast processing of the optimized operation of the system, we have managed to have throughputs of several tons of equipment scanned per hour. Now, for the topic of lifecycle analysis in the context of GRINNER, just a high level here term of what is lifecycle analysis. It's a methodology used for evaluating the environmental impacts associated with all the stages of a product's life. And why is it important for us here? It's important because it ensures that the proposed solution doesn't shift the environmental burden elsewhere in the chain. So yes, it's good that we're going to develop the GRINNER system, but if it adds too much cost in terms of environmental impact, maybe we should think about it some more. It also quantifies the environmental and cost benefits of the systems, and it can be used as a market statement as well, and then can also support policy shift justification in organizational and government level. Now, the procedure we follow in the GRINNER context is that we evaluate the environmental impact of current operations without intervention, so what is currently being done. We will then develop a life cycle inventory through a cradle-to-grave approach, which I will describe in the next slide. We will then quantify the environmental impact of the solution in terms of greenhouse gas emissions, energy use, material toxicity, and recyclability, because obviously toxicity and recyclability is a point to examine here in the green solution, because we're using X-rays. X-rays need shielding using lead material. So this is something we need to look on. And we will then compare the results of the analysis with those of current operations and identify where most environmental trade-offs occur and how we can minimize them. Now, for the cradle-to-grave analysis approach that we follow, we go on a clockwise direction here in this icon. First, we need to calculate the emissions produced by the raw, or estimate the emissions produced by the raw materials used in the GRINNER system, which we inherit because this occurred through raw material extraction. We then estimate the emissions taking place during the manufacturing of the system. We then also include the emissions produced during transportation of the raw materials to the production facilities and of the final system to the operator. Then we also take into account emissions occurring during the lifetime of the system while it is being used. This is the energy used, for example, components that are replaced during maintenance and any consumables. And then we also include the recycling, the greenhouse gas emissions due to recycling or the destruction of the materials, so materials lost. Now, the impact we expect for GRINNER is that it will increase the number of batteries recycled, because currently only 5% of lithium-ion batteries are successfully recycled globally. It will help to avoid greenhouse and toxic gas emissions due to plant fires. On the financial side of things, adoption of the GRINNER system by only 6% of the market could save up to 3 million in that industry, in the recycling industry. And it will also help improve the efficiency of waste sorting by 30%. And in the societal impact side of things, it will reduce the risk of worker injury due to fire, also reduce the worker exposure to toxic materials and fumes. And just to summarize my presentation, addressing fires in waste electrical and electronic equipment recycling plants is very important, but it must be done responsibly. And the LCA is a very powerful tool that can be used to assess solutions such as GRINNER, but also highlights areas of improvement in its development and manufacturing. And the requirement for sustainable solutions is now more important than ever in this age that we live through. And LCA contributes to decision-making by looking beyond just the immediate fix and considering a product's full life cycle. And this concludes my presentation. This is my name and my contact details if you would like to contact me after this webinar. And make sure to follow us in the next episode, where we will present data scarcity and how do we deal with it in the GRINNER project context. And yeah, thank you very much, and I'll be happy to take questions.
Thank you very much, Nikos. And thank you very much to all the speakers for their interesting presentations. Now we have time for an open Q&A sessions. So if there are any questions, please jump in or write them in the chat. I've seen that Roberto and Federico already answered some questions in the chat. I just wanted to check if there are something else. For example, I saw that before Kapil wrote to Fredy, what is the per day thresholds upper and lower of your system?
So I guess Kapil talks about the recovered material in tons, I can say that our system can recover about 45 to 50,000 containers per 7 hours of use. That equals to 1.5 tons per material in one duty. That one duty is 6.5 hours. Right now we have we don't have operated the system more than one duty because we are not in the seasonal peak, but we believe that it can happen. So I can say that the minimal threshold is 1.5 tons and up to 4.5 tons of recovered material. And as I can see, another question regarding the PRMRF is what are the main technical challenges that we encountered while automating the material recovery? Well, the main challenges that we had is is during the pre-sorting. What happens before the recyclables enter the container? I mean, we have to make it to make it to units, and we have to have small containers entering the container. We have to put away all the big cartons and foils, and I think that's the biggest challenges in order to automate. That's the thing that we can't automate very easily, and we have to ask from the citizens in the remote places to do some pre-sorting in their waste.
Thank you very much. So there are some other questions. Firstly, for CLARUS. So how could the Green Deal Index be adapted for industries beyond the food sector?
Yes, thank you, Ludovica. Thank you for the question. I think that the Green Deal Index can be easily adapted beyond the food sector because is an indicator that is built following an aggregation method that can be replicated for any type of natural resource consumed and any type of environmental sustainability data. So if, for example, for the industrial pilot of CLARUS, the main interest is on optimization of energy efficiency and water consumption, maybe for any other food company, the priorities could be different, but the selection of the indicators, the aggregation method, the weighted method, and also the normalization method can be totally the same. So I think that the adaptability is very easy. What could be an issue is the comparison between different type of companies or different type of sectors. But this is, I would say, a general issue that characterize many sustainability metrics and many sustainability assessment methodologies. So the difficulties could be to compare different Green Deal Index that are measured in environment that are not the same. But I repeat, the calculation process can be easily adapted to any manufacturing industries, and also, in my opinion, involve a different scale of dimension. So considering the hierarchy level of the indicators that we have discussed before, of course, this calculation can involve different of this level. Regarding the second part of the question, I don't see any possible radical changes to the CLARUS solution if we change sector. I mean, the differences could be on the variables, as I said, that are selected to be optimized, because maybe in other sectors there are other variables more interesting respect to the variables that we have analyzed in CLARUS, but at the end, the presence of the GDI within the CLARUS solution, in my opinion, can be easily replicated in many sectors.
Okay, thank you very much, Roberto. And also, connecting to this question, there is a question for ALCHIMIA and the LCA methodology. So do you think LCA is accessible to small, medium enterprises or not? And also, what do you think are the barriers that companies encounter when they want to introduce these sustainability frameworks?
So I think, of course, the spread of LCA in small and medium enterprises have some barriers. The first one is the availability of data, specific databases. Usually what the companies ask to our group is to create some tools instead of doing a consultancy that calculates the environmental impact of their process and just produces a report. They rather prefer having some tools that can be at different levels of complexity, but something that can be customized and really used by the companies. Also, another limitation is, let's say, the regulatory framework, because you know that when you have doing an EPD or you follow the product environmental footprint, there are some very big differences in terms of methodological choices. So sometimes companies can be confused, and of course they shall be guided to decide what is the most suitable framework to which they can that they may follow, let's say.
Thank you very much, Federico. I don't know if also Roberto wanted to add something regarding the barriers that you have encountered when adopting the methodology for CLARUS in the pilots and also in the companies now. If you wanted to add something regarding this.
Yes. Well, first of all, I agree with all the comments of Federico. In terms of CLARUS solution, I think okay. Maybe the main barriers that we have encountered are, from one side, on a technological perspectives in terms of data gathering and data management, because of course if we think to the CLARUS solution and the possibility to develop a unique platform with high communication capabilities, of course, the application of this solution and the development of this solution depends a lot from the digital maturity of the company. Of course, because if we want to install sensors, gather data, manage data, build a data space, and elaborate data through artificial intelligence and so on, of course, this depends from the readiness from a digital perspective of the company. And of course, this can be a barrier, because less digitalized is the company, more investment it will do in order to develop this platform. So the classical, barrier and issues that involve LCA or any other sustainability matrix in terms of data detection, data gathering, and data analysis can be helped a lot by the installation of this type of digital technologies. The other main issue, of course, is always about the comparison of the results, because the complexity of the sustainability paradigm means, as we have said more than one time in all our presentations this morning, involve different type of variables to be managed. So compare with the same indicators, as we have said before, different parameters elaborated and gated in different industrial contexts. Of course, these represent a possible issues in terms of comparison. So these are the main barrier that I would like to highlight.
Thank you very much, Roberto. We have a last question, I think, for GRINNER. I think it's related to what you, Nikos, were talking about before. So the life cycle assessment methodology you're using in GRINNER, sorry. So how do you measure the environmental benefits of reducing fire risks compared to other sustainability actions?
Yes, so we have some estimates about how many fires occur, for example, because we have an end user. So we have a recycling a plant partner in the project. So they can give us some estimates on that. And also what, for example, materials are burned during these fires. But of course, these are estimates. We cannot be sure because there's a random event and each plant differs in the materials they process. But yeah, I don't know if that answers the question. In regards to the system itself and how it helps is okay by reducing fires, and we know the impact it has because we have the bill of materials. We know exactly how much it impacts the environment to be built and how much energy it uses, for example. For the impact of the system, it's easy, therefore. But yeah, we can only estimate about how much benefit it brings. Mm-hmm.
Makes sense. Thank you very much, Nikos. And thank you all for your questions. I don't think we have any other questions. So please let me thank you everyone for participating to the webinar, to the speakers. I think we had very interesting insights on life cycle assessment used in CLARUS and ALCHIMIA, a proof of the first portable material recoverability facility, and also how to use life cycle assessment, not directly to assess sustainability, but to see how a solution can be convenient or not, like in GRINNER. So I wanted to promote also our next webinar, as Nikos was saying, from the cluster. So I'm sharing the link to register in the chat. And yes, thank you all for participating, and I hope I can see you also in the next webinar on May 9th.
Thank you very much, Ludovica.
Thank you very much.
Thank you, Ludovica.
Thank you very much.
Bye.
Bye-bye, everyone.
Bye.
Bye-bye.